guys, you're going to need to make sure that you have your periodic table for this one. We're going to do more Lewis structures, so these ones are going to be a little more complicated. We're also going to do resonance structure and formal charge, which is always going to be based on your initial drawing. Okay, so resonance is when you have two or more valid Lewis structures that are drawn for the same compound. So lots of different compounds have those. I'll show you some in a minute. Formal charge is a way to keep up with what charges specifically are per atom instead of for the whole thing. Like last video, we did NH4+. So it looked like this. So instead of having this plus on the outside, we would put that plus charge on a specific atom to show which one had the charge. Okay, so for resonance, like I said, there were two different structures for the same molecule, and they're only going to differ in the position of electrons. So you can see in these two ozones at the bottom, you've got a double bonded oxygen on both of them, but they switch spots. And a lot of the time in resonance structures, that's how you can tell there's going to be more than one, is that there's one double bond, but it could be on other atoms in the molecule. So resonance is not one or the other. In reality, it's both happening, and it's kind of like a hybrid. So here they're showing, the hybrid between two types of dogs. Sometimes we call these mixed breeds. I have a German Shepherd Husky mix, and we're hoping she won't have problems like a purebred will, because it's the best of both worlds. It's also kind of like that in electric and gas cars. So that hybrid is the best of both worlds. It can go farther than a generic electric car, but it's more eco-friendly and efficient than a gas car. So hybrids are going to be the same for resonance. And again, in reality, it's going to be this piece. Really on a test or a quiz, I would say which of these has resonance or how many resonance structures. So you're going to need to be able to draw them, but not necessarily to show me them on a test or a quiz. So the first thing when you're doing resonance structures is to just draw the first structure. So draw one, and then we can see what we can do. So here we've got a nitrate ion. N goes in the middle. Remember, the least electronegative. Then we count valence. I have 5 plus 6 times 3. Remember that negative means add 1. So I've got 24. We draw our lines, and then I subtract. That's 6. I've got 18 left. Okay, remember they go on the outside atoms first. 6 dots per, because of the line already has 2. Remember, we're trying to get to 8. Okay, once I do that, I have now distributed all of my electrons. So then you check, does everything have 8? All the oxygens do, but nitrogen only has 6. So what I have to do is I have to make a double bond somewhere. Don't forget what charges you bracketed in. Now, what's to say I could not have done a double bond like this? And there's nothing to say I couldn't do that. Or a double bond on the far left oxygen. The key is something like this has 1 double bonded oxygen and 2 single bonded oxygens. And these little arrows indicate that there's resonance in between them, and that's just showing that it's an intermediate within all of them. So as soon as you've moved your double bond to all the places, that's generally as many as you have. So sometimes a quiz question may say, how many resonance structures are in NO3-? And in this case, you would say 3. If we had NO2-, so first, again, we draw NO2. I've got 5 plus 6 times 2 plus 1, so that's 18. I've used 4, 14, Dot it up. 6 on each. And then I've got 2 left. They go on the center. This is the first time we've seen ones that go on the center. Okay, I can't write there because my little box is there. Minus 12 is 2. Okay, so I do my brackets, but we didn't check to see if everything had 8, and it did not. So one of these oxygens needs to double bond. I do want to tell you, often students will put extra 2 electrons on the nitrogen. Well, you don't have an extra 2 electrons because you've already used them. So you have to be careful and count all your electrons. That is the biggest part of this. Okay, got to do the same thing for resonance on the other side. So we've got to flip that double bond. Then we're good. So nitrite has 2 resonance structures. Now we're going to go into formal charge. So formal charge is normally used on resonance structures. And the thing with resonances, they have to have the same connectivity. So the way they're connected need to be the same. Only electrons are moving, not anything else. And then they need to have the same number of electrons because otherwise they're not resonance structures. Okay, also they need to be proper structures. So if you don't have, like if you have something that has 10 electrons on an outside atom, that's not a proper structure. Okay, but the key to resonance for formal charge is that the formal charges must all total the same amount. Like the sum of them needs to be equal. The better structures are going to have fewer charges, smaller charges, and if need be, the more negative one needs to be on the electronegative element. So remember, those are the arrows like this. We did talk about that last video. So the equation for formal charge is per element. You do it for every element in the structure. Okay, you do the number of valence electrons which you find on the periodic table. You subtract the dots, and then you subtract the bonds. I will tell you, the book likes to use halves, and I got rid of that. So like here for hydrogen, it's got 1 valence, it's got 0 dots, it's got 1 bond. So this one we would say is 0. Fluorine, 7 valence, minus 6 dots, minus 1 bond. So this one is also 0. Remember, we want them to be 0. That is the most stable configuration. Also, hydrofluoric acid shows no charge. So you need to make sure when you draw it, there's no total charge shown. The sum is 0. Okay, so here they're doing the other ones. For sulfur dioxide. For this oxygen, I've got 6 minus 4 minus 2, so that one is 0. This oxygen is different. 6 minus 6 minus 1. So this one is negative 1. And then the sulfur is 6 minus 2 minus 3. So this sulfur is positive 1. Notice the sum still adds up to 0 for the whole structure, which is good, but some of them do have a formal charge. So here we're comparing hydrocyanic acid. We're trying to base it on the formal charge, which structure is better. And if we look down here, this is the better structure, and it's because everything is 0. That is the best case scenario. While structure B, the sum is 0, everything's not. And so it wants the electrons to be distributed based on the valence electrons, if possible. So here, again, we're trying to, first off, assigning formal charge. Then, which form is best is the correct structure. Okay, so for this one, we do need to find the formal charge for all. And I do sometimes ask questions like this in person. And if you don't do formal charge at all, you're not getting the point, whether you choose the right one or not. Because the question was about formal charge. Okay, so in A, O is 6 valence minus 6 dots minus 1. So that one's a negative. C is 4 minus no dots minus 4. So that's 0. N is 5 minus 2 minus 3. So that's 0. Okay, and all of that does add up to negative 1. For B, oxygen, 6 minus 4 minus 2. So oxygen is 0. Carbon is 4 minus 0 minus 4. Y'all, and if you notice, carbon normally does not have dots. That's because it wants to have those 4 bonds. Nitrogen in B is 5 minus 4 minus 2, so that one's negative 1. C, oxygen is 6 minus 2 minus 3, so that one is plus 1. Carbon, 4 minus 0 minus 4. And this nitrogen is 5 minus 6 minus 1. So that's actually negative 2. So once we get all the formal charges, we can eliminate 1. We can eliminate C. And that's, yes, the sum adds up to the correct number. However, those values are bigger than the other ones. So we're left with A and B. Some of you may say, hey, A and B are the same because they have 2 zeros and a negative 1. However, we're looking for the negative to be on the more electronegative element, which is the one closer to fluorine. So the element closer to fluorine is oxygen. So that's the one that needs that negative charge. Okay, it's more likely to gain electrons than nitrogen is. Of course, if you have any questions on this or need help, I'll be happy to send you some stuff on it. Same thing here, assign formal charge. So I've got negative 1, plus 1, 0. 0, plus 1, negative 1. Plus 1, negative 1. Positive 2. Hang on. 5 minus 6, negative. Okay, so that one's also a plus 1. I was like, something isn't adding up on this last one. But 6 minus 5 is plus. So again, on this one, you can automatically get rid of C. We're looking for the more electronegative element to have the negative, so that would be B. Okay, so for organic molecules, you will have to draw some organic molecules, and it'll give you a structure like this in mastering chemistry. Okay, you have to then, so this is a skeletal structure, you have to count total valence, you have to do the drawing, the lines and the dots. So let's do total valence. I've got 4 from carbon, 3 times 1 for hydrogen, 5 and 2 times 6. So I've got 4, 7, 12, 24. Okay, I do my bonds. Please do not do any crazy bonding. We're just going to draw single lines between the elements. And I got 2, 4, 6, 8, 10, 12. So I've already used 12 electrons. Remember, all of your dots go on outside atoms first, but they cannot go on hydrogen, which means all 12 of them are going to go on oxygen. Okay, we look, does everything have 8 except hydrogen? And the answer is yes, except nitrogen. So for nitrogen, I need to move a pair. It can either be like that, or like that. Okay, so I've got 2 resonance structures, assign formal charge to both. So carbons and hydrogens are normally going to be 0. The only ones here that are going to have a formal charge are either nitrogen or oxygen. So this oxygen's negative 1, 0, plus. This one is 0, negative 1, plus 1. So on Mastering Chemistry, when you're drawing these, there are little buttons at the bottom. They may actually be at the top, but there's a little plus and minus button, and all you do is go click on that specific element with that selected. And again, if you need any help with that, please let me know. I will be happy to get on office hours with you and help walk you through that because it is a little confusing, right? Just let me know. Okay. Also, there are some exceptions to the octet rule. So there are some elements that'll have an odd number of electrons. The only one y'all are going to encounter is nitrogen. So in the event that we were to do NO, which has 11 valence, got NO, I've already used 2, so that's 9. Okay, that's not good. We need a double bond. Got 2, 4, 6, 8, 2, 3, 4, 5, 6, 7. Okay, so this would be how it looks. Again, the only time you're going to encounter this is with nitrogen having the extra dot. Please do not put the extra dot on anything else. The reason nitrogen is okay with it is because it's used to having 5 valence electrons. Okay, also, boron will have 6. It's very common. Boron has 6. And very commonly, I have students that want to give boron 8. But boron cannot hold 8. It only gets 6. And of course, we'd already talked about hydrogen has 2. There are expanded octets, which means more than 8. And it is only up to 12. And it's only on the central atom. It is very important that you understand it's only on that central atom. Okay. Also, the only ones that can have expanded octets are nonmetals that are in period 3, 4, 5, 6, and 7. So, not row 2. Carbon cannot have expanded. Oxygen, nitrogen, and fluorine cannot. But silicon can, and phosphorus can, sulfur can, bromine. Okay, anything in row 3 and down on the periodic table, like physically down on the periodic table, can do that. It's because they're using empty space from the d orbital. So they're just moving electrons around to make more space into other orbitals. Okay, so XeF2. Xe goes in the middle, least electronegative element. First off, it's a noble gas. It is super electronegative. So I've got 14 plus 8 is 22. I've used 4. I've got 18. If I do 6 on each of these outside ones, that's 12. So I've got 6 left. Once you've got this situation, some students like to double bond. You only double bond when you don't have enough, not when you have extra. So I'm going to put all 6 on xenon because xenon is in row 5, which means it can have that expanded octet. Yes, it's a little awkward, but that's how it is. Please do not put dots by the lines. Like, don't do this. Because that, to me, shows me that you're sharing them, not that they're separate lone pairs. Okay? Also, please make sure that they're paired. Don't do this. That is not how they are. If you did that with shoes in your house and they were across the house, you may never find the other shoe. Okay? So, electrons come in pairs. Make sure you always keep them that way. Let's do another one. XeF4. Again, Xe in the middle. F, 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 F. I've got 8 plus 4 times 7, so that's 28 plus 8 is 36. I've already used 8, so that's 28. So with 6 dots on each, that gives me 24 used. With that 24 gone, I've got 4 left. At that point, where do they go? The only place they can go is on the central atom. Again, in pairs, try to keep them separate, like separate from each other, the pairs. Don't put them together. Sometimes I have students triple them up. Don't do that. They come in pairs. Okay, we're not going to do that one. There won't be any like that on the test. Now we're going to shift into bond energy, and this will reappear in Chapter 9. So I may only have one question on this exam. But when we come to Chapter 9, it's going to be more important. Okay, so the amount of energy in the gaseous state, so we got to be in a gas state, that takes to break 1 mole is called that bond energy. So breaking 1 mole of a bond is bond energy. Bond energy is going to be in kilojoules. And something to keep in mind, a stronger bond, or one with a higher bond energy, will share more electrons. So if we look, carbon triple bond takes more energy to break than a carbon single bond. That's because when more things hold it together, it's harder to break. Also, the shorter the covalent bond, the stronger it is. We'll talk about that in a minute. Here is a table of bond energies in the event you need to calculate them. Okay? If you need to calculate them, you will be given them in a problem. Not for mastering chemistry, but for a quiz or a test. So to calculate bond energy, it's the change in enthalpy, which is delta H. Change in is delta. So bonds broken are the reactants. And those bonds formed are going to be the products. Okay, this little squiggly looking E, that just means sum. Okay, so we'll talk about that as we go through a problem. I do want you to know for bond strength, single bond is the weakest. Triple bond is the strongest. Okay, bond strength, that's how much energy must be added to the bond to break it. Also for bond length, triple bonds are going to be the shortest. So it's going to be triple is shorter than double is shorter than single. And you just determine the bond length by half the distance between 2 nuclei that are bonded together. I won't ask you the definition, but you will need to know which one is strongest, which one is shortest. Okay, here is also a table of bond lengths. And you can tell here, when we're comparing carbons, carbon triple bond is shorter than carbon single bond. We can even see that in nitrogen. Carbon triple bond is 110, carbon single bond is 145. Okay, and something in general, as bonds get longer, so those are the single bonds, they're going to get weaker. They're going to be easier to pull apart. And just think of that one, the easier to pull apart. If there's only one thing connecting you, it's easy to pull apart. When there's more things, it gets a little harder, more complicated. Okay, it doesn't look like we're going to be doing any calculating of bond strengths now, but it will appear in Chapter 9. Okay, y'all have a great day. That's it.